Hi class. So this section we're going to be looking at reactions of acids and bases. So this is just showing an example of stomach acid, which has hydrochloric acid in it, and it's around a pH of 2. But this section is actually, we're going to deal with looking at balanced equations for reactions with acids with metals, carbonates and bicarbs, and then bases. And we're also going to look at titration. Last part of this is going to be about titrations. So acids react with metals to produce a salt and hydrogen gas. They can also react with bases to produce a salt and water. And when acids deal with bicarbonate or carbonate ions, they produce CO2. And a salt is simply a comp of the leftover anion and cation that was not involved in whichever one of these reactions that was reacting with the acid. So let's take a look at acids. So acids will react with metals. As you can see here, these are single replacement reactions. And then we have magnesium metal, and on the bottom we have zinc metal. And when they come into contact with HCl, they will kick the hydrogen out. They will kick the hydrogen out and replace it. And hydrogen, in its natural state, is a diatomic gas, so it will leave this reaction. That's what you see the bubbling in the pictures as a gas. It's leaving the chemical reaction. It's been pushed out. Now, when acids react with carbonate or bicarbonate, they produce carbon dioxide, salt, and water. And so when you tend to see, if you ever see a reaction with an acid and a carbonate, you should know that the end result is going to be CO2, some kind of salt, and a water. Same as bicarbonate. And these are a double replacement reaction. Here, the last one is a double replacement, is a neutralization reaction. This has to do with an acid and a base. And when you have an acid and a base together, it results in water and a leftover salt of whichever anion and cation was not used to produce the water. This is the one we're going to focus on right now. So in a neutralization reaction, you can see that the hydrogen ion from the acid attaches to the hydroxide ion, and it produces the water, leaving a salt. In this case, it is actually salt. It's sodium chloride, but it could be whatever the leftover ions were. In this, the middle one, if you leave it out, if you pull this apart into ionic form, you will see that the chloride is on this side and the chloride's on this side, the sodium's on this side, the sodium's on this side. And because they're on the same side and nothing's being done to them, they're spectator ions. So we can cross them out, and what we're left with is only the ions that produce the water. And at the bottom one, so this middle one is called a total ionic equation, and this bottom one here is the net ionic, meaning it only involves the equations that the ions that have to do with producing the water. So in this case, we have the hydrogen ion and the hydroxide, and that produces the water. So I put these in here against my better judgment. These are teaching you how to balance reactions, but you guys already know how to balance reactions, or you should have a fairly good idea. I don't like the way they're doing these. I sometimes am not sure if I should have given you guys these slides, because how they want you to do it is balance everything, but leave the salt out to the very end, and I kind of protest this. Because if you're going, I added that. If you're going to balance, you should be able to see the whole thing. I know that they're trying to stress the salt. I don't think that this is the right way. But again, I want to give you the slides that they've given me. If they help somebody, so be it. But by now, you definitely should know how to balance reactions. You should definitely know what these steps are to get to the end for this. So I'm giving these to you, but I don't like that they're leaving one portion out until the very, very end. This is not something I agree with. If you have problems balancing reactions, these are good then, because they're giving you the answers. Go through them. If you need help, you can always contact me. Okay, so now let's look at antacids. Antacids are hydroxides that are not soluble in water, yet when you take them for an antacid, it will neutralize the excess acid. So they do their job, and then they leave the body. Here is a look at some of the compounds and what the bases are made of those antacids here. You can see Alka-Seltzer, Pepto-Bismol. I grew up, Maalox was the only thing in our house. I don't even know if they make that anymore. I do not know what this is at all, and it keeps showing up. Maybe I've never seen it or paid attention. Okay, this last section is a titration. This is a very good section. No matter which chemistry you take, titrations will follow you through it all. I teach a different chemistry. It's got 3 different courses to it, and every course of that chemistry are titrations. So you never escape a titration ever in chemistry. They like titrations. So let me explain this. It is a laboratory procedure used to determine the molarity of an acid. So if you wanted to know a concentration of an acid, this is a good way to do it. You have a base, and you would know the volume, the concentration, and the volume that you're going to use in the titration. And what you would do is you would have a specific volume of that acid. You would add a few drops of indicator. And here you can see that this is phenolphthalein. It is clear in acidic conditions, and it turns pink and into almost a dark purple as the base increases. And we're going to do this to an endpoint, which I'll talk about in a little bit. So we have a specific volume of acid, but we don't know what the acid is. We know how much volume of base is in the Brett and then we have increments to see how much we've used. And we also know the concentration of this, the molarity. And what we'll do is the base is added to the acid until it hits the endpoint. If you do it right, you hit the endpoint well. If you don't, you end up with a very dark purple, pink purple, and that's 90% of my classes, because this takes a lot of patience. And I have found, no offense, a lot of chemistry students have no patience in the lab. So the indicator is added to identify the endpoint. We specifically pick an indicator that will match the pH that we need it to be neutral, to show neutralization. So we have an acid, we have a base, and we're waiting for it to be we go through this until it's neutralized. When it's neutralized, we pick an endpoint, an indicator that will match the endpoint that will show when our moles of acid and moles of base are equal. If you go past that endpoint, then now it's no longer equal, but you'll still have to finish the titration. This is why students don't like this, because unlike other labs, this is visual right from the start. If you mess up, you see it right away. And one drop could push you way past your endpoint. So this is a very, very sensitive technique, and that's why a lot of students don't have the patience for it, because they don't want to go drop by drop by drop. So here at the end point, the moles of the base are equal to the moles of the acid in the solution. We already know the concentration of the base. We will know the volume of the base used, and when it's hit the end point, and then from that we can calculate the molarity because we know the volume of acid that's in the flask. So let's put all that to calculations to make you understand. These questions, when you first read them, seem overwhelming. They are not, and don't let that get in your head. They follow simple steps if you pay attention. Okay, so the molarity of an HCl solution is 18.5. Let's just say it. What is the molarity of an HCl solution if, that should say is, 18.5 mils of 0.225 molarity of sodium hydroxide is required to neutralize 0.0100 liters of HCl. We need a balanced equation because we're going to need to know what the ratio is of the acid to the base. Luckily for us, all the coefficients on here are 1, so everything is a 1-to-1 ratio. We're given information, and from this information we can now make a connection. So what we're trying to do is a stepping stone to get to the answer, and the answer is the molarity of HCl. So here we start with the volume of sodium hydroxide. We need to get rid of that, so we convert the mils to liters, and remember this is moles over liters, so that will cancel out. We are now left with the moles of sodium hydroxide. This is where the ratio comes in. So the moles of 1 mole of sodium hydroxide is equivalent to 1 mole of HCl. We will now be in our moles of HCl. We divide that by the volume of HCl, and that will give us our molarity of HCl. So here are our quantities and conversions that we're going to use, and then we plug it all in. So we start with the volume of sodium hydroxide. We use the conversion to get it to liters. We use the liters from the molarity of the sodium hydroxide, cancels out, gives us some moles. Now we can cancel out the moles of sodium hydroxide because we've done the ratio. Gives us moles of sodium hydroxide, of HCl. And we take the volume of HCl, and it gives us a molarity of 0.416 molar HCl. Let's do another question. Okay, what is the molarity of an HCl solution if 25.5 mils, oh maybe that makes sense, of 0.438 molar sodium hydroxide is required to neutralize 0.025 liters of HCl. So this is very similar to the first one. So hopefully going through a second time, you start seeing why we're doing what we're doing. So here we're given all the information, and most importantly, we need the equation to make sure what the mole ratio is, because they're not always 1-to-1. So here we go through the same steps. We have the volume, and then we use a conversion to get to the moles of sodium hydroxide. We use a mole to mole ratio, which is 1-to-1. By now we should end up with the moles of HCl, and then we divide by the liters, giving us the molarity. So here we go again, 25.5 mils of NH. We cancel NaOH, cancel it out, cancel out the volume. We get to the moles of sodium hydroxide, set that up with a 1-to-1 ratio. We are now in moles of HCl, and we take the volume of HCl, and that gives us 0.447 molar HCl. Not difficult, but if you set up the units right, it will get you to the very end. Just got to make sure you set the units up right. Just take your time, and after a while, this will make sense. They're not as overwhelming as it looks. Thank you.